In this presentation, we're going to talk about bond and anchorage and development length of reinforcement in reinforced concrete structures. By the end of this presentation, you should be able to explain the importance of providing adequate anchorage and development lengths, differentiate between two different types of anchorage failures, use ACI 318 to calculate development lengths and splice lengths, design required bar details to satisfy ACI 318 development length requirements, and recommend ways to decrease the development length. We need our reinforcement to have a sufficient development length so that it can achieve the yield stress, which we assume. If we were to place a rebar inside a smooth tube in a beam, that rebar would not be able to develop any tension unless we put some kind of anchors at the ends. To develop tension, we need to have contact interaction between the steel and the surrounding concrete, or we need to have some kind of anchor at the end to transfer the stress there. Regions where there's excessive cracking may not provide enough interaction to properly develop a bar. So in a simply supported beam where we have point loads towards the outside, we may have a region with that develops excessive cracking where the bars don't develop. So we need to make sure that the reinforcement can develop the yield stress by the time it exits the uncracked zone here. So the question here is, can Fy be developed in this available length? If we don't provide sufficient development length, it can lead to a brittle failure of our structure. Here's an example of a high mast pole where these number 11 bars weren't properly developed. So you can see the bars just pulled out and the high mast pole fell. If a bar does not develop or doesn't have a sufficient development length, it cannot reach its yield strength, and therefore you won't have the yielding behavior of the steel. So you're going to have a more brittle failure because the yielding behavior and our yield plateau and strain hardening region is where we get our ductility from. The bond between the reinforcement and the concrete is primarily provided by the deformations and the bearing of the concrete against those deformations. So if we tried to pull a piece of rebar out of a block of concrete, we would have our deformations in that rebar, and the bond between the rebar and between the concrete and the rebar would be provided because the concrete is bearing against these deformations. So you can see a deformed bar would provide much higher bond or much larger bond than a capacity than a smooth bar. So that's why most of our, or all of the rebar that we use will have deformations on it to provide that bond between the concrete and the rebar. One way to test the bond capacity between the rebar and the concrete is doing just a pull-out test. So shown here is a schematic of a simple pull-out test where you have these supports bearing against the concrete away from the point where you're doing the pull-out test. If you have these supports too close to where you're pulling out, then the compression provided by the supports and that reaction will influence will provide active confining stresses and influence the bond performance here. So anyway, you embed a piece of rebar, you pull out, and you see the force and the stress required to pull out the bar. You are often looking to see if the failure occurs in the bond or if you're able to yield the rebar and fracture the rebar while keeping the bond intact. Development failures can occur in one of two possible ways. Concrete can split at the location of the reinforcement, and when this splitting occurs, it will cause, the two sides will split apart and the rebar can just pull out. Shearing can also occur on the plane between the reinforcement and the concrete, and then the reinforcement just pulls out. So we can have shearing right along this plane outside the deformations. And in this case, the reinforcement will come out with all the concrete kind of embedded in these trowels in between the deformations. In a splitting failure, the resistance depends on the tensile strength of the concrete, so it's proportional to the square root of F prime C. Our resistance is then equal to some constant K1 times the square root of F prime C times our development length. And the goal is that we develop the yield strength of our bar here. So the goal is to have the area of our bar times the yield strength of the bar equal to this resistance. So then we can calculate the development length here, and we can see it's proportional to the yield strength over the square root of F prime C and times the area of the bar. Similarly, for pull-out failures, our resistance depends on the pure shear strength of the concrete right along this shearing plane. So our resistance is equal to K2, a constant, times the square root of F prime C. To develop our resistance, we again want to set this AB times Fy equal to this K2 times square root of F prime C times the area of our shearing plane. So then we can solve for LD, and you can see again it's proportional to Fy divided by square root of F prime C times the diameter of our bar. So you can see both of these have a similar form. ACI 318 simplifies the expressions from the previous slide and combines them into the equation shown here. So this is the detailed expression to calculate the development length of a reinforcement with diameter d sub b. So you can see we have a similar form, Fy divided by the square root of F prime C, and several factors, which we'll talk about later, and this bottom term, which we'll also talk about later. But this expression accounts for both splitting and pull-out failure types. So a pull-out failure, the shearing around the bar and just pull out of the bar, and a splitting failure either to the bar to the cover or between bar and bar. You need to make sure that you have a sufficient development length wherever you're calculating your tension and compression forces, and you're requiring, or you need your strength. So whenever we have ASFY in our reinforcement, we need to make sure that we can develop Fy on both sides of that section. There are a number of different sections that are critical or can be critical. I'm going to go over a few on the next couple slides, but again, these aren't the only cases where you need to check development. The first is at the end of a cantilever beam. The maximum moment is at the end of the beam, or sorry, at the interface between the wall or column and the beam. So this is where we're depending on Fy. So we need to make sure that we have a sufficient development length into the wall or the column. So we need to provide a hook or a straight bar extending into the adjacent beam if that's the case. And we also need to make sure that we have a sufficient development length into the cantilevered beam. So we need to check this distance towards our point load at the end. So these are the two instances where we need to check our development length in the end of a cantilever beam. Another common example of a place where we need to check our development is when we're cutting off reinforcement in other beams. Often we'll cut off our reinforcement before the end of a beam to try to decrease the amount of reinforcement in the beam. But if we cut it off, we need to make sure that we have a sufficient development length. So when we cut it off here, we may be depending on the development of the bar that we didn't cut off to develop yield. So we would need to check that development length. And we also need to make sure that we extend this bar far enough away from the point of maximum moment so that we can develop the bar that we are cutting off. So these are two examples where we need to make sure that we have sufficient development when we're cutting off reinforcement in a beam. The other common location that we've talked about already in this class is when we're anchoring ties in the strut and tie method. So when we have a tie, we're counting on the yield strength of that reinforcement when we exit the extended nodal zone. So right here for the top bar and right here for the lower bar. So we need to make sure that we have a sufficient development length from the back of that bar or the back of the hook here to when we leave the extended nodal zone to develop Fy. If we don't, then we either need to increase the hook or look at some kind of alternate anchoring, like a headed bar or a steel plate or something. On the next slides, we're going to look at how to estimate the required development length using ACI 318. The first requirement I'm going to highlight is a basic limit. So all of our development lengths for straight bars in tension need to be greater than or equal to 12 inches. So if you get a value in any of these equations that we're going to go through less than 12 inches, your minimum development length limit kicks in. So you'll have a 12-inch limit. In ACI, we have a simplified procedure and a detailed procedure for calculating our development lengths. So shown here in this table is the simplified formulas for the development length of a straight bar in tension. So you can see based on the spacing and cover of the bar and based on the bar size, you can come in and choose the correct equation to start with. On this slide, I'm showing you the detailed formula for calculating the development length. The detailed formula will typically give you a shorter development length than the simplified formula. So the idea being that if you do more calculations and a more detailed analysis, you'll get some benefits and get a shorter development length. So you can see here we have some additional terms, which we'll talk about, this CB plus KTR over DB, which I'll go over, but the CB is dependent on the cover and bar spacing, and the KTR here is dependent on the area of our transverse steel that crosses the splitting plane. So the idea being that if you have more reinforcement crossing the splitting plane, you're going to have a shorter development length because it'll be less, it'll take more force for that splitting plane to develop. When looking at the ATR and CB terms, we need to consider what splitting plane is going to control the failure of our development. We can either have a splitting failure that occurs between the bar and the bottom face of our beam, or we can have a failure that occurs across the level of the reinforcement from side face to side face. If we have the splitting failure between the bar and the bottom of the beam, our area of the transverse reinforcement crossing that splitting crack is going to just equal the area of the bar, because there's only one leg of reinforcement crossing the splitting crack. You can see that there's only one bar involved in this splitting failure. So in this case, our N is equal to 1 bar. And the CB is the distance between the center of this bar and the outside face. So CB would be half of the diameter of the bar plus the diameter of our stirrup or tie plus our cover distance. When we're talking about a side face to side face splitting failure, we have two bars crossing the splitting, or two transverse bars crossing the splitting plane. So we have two bars crossing the splitting plane. And in this case, we have 1, 2, 3 bars involved in that splitting crack. So our N is equal to 3. If we had more bars involved in this splitting crack, so more bars in this layer, then our N would just be equal to the number of bars in that layer. And we can calculate our CB based on the distance between the side face and center to center spacing of the bar, which we'll look at in an example. Additionally, you can note that ACI 318 has a requirement that our square root of f prime c must not exceed 100 psi in these equations. On this slide, I'm showing you some of the modification factors for our development length equations in ACI. The first one is the top bar factor. If we have more than 12 inches of fresh concrete below the horizontal reinforcement, then we're going to need to take our development, or it'll increase the development length. So in this case, water rises during the initial curing, and it increases the development length of bars that are placed with more than 12 inches below. So that's our 1.3 there. Otherwise, we use a top bar modification factor of 1.0. The next factor takes into account the reinforcement grade. So typically right now we'll use grade 60 reinforcement, so this psi factor will be equal to 1. But if you have higher grade steel, then you need to increase this reinforcement grade factor. The last factor is shown on this slide is the epoxy coated bar factor. If you have epoxy coated or zinc and epoxy dual coated reinforcement with the lesser covers, then you need to magnify the development length by 1.5. Other epoxy coated bars 1.2, and for all uncoated bars 1.0. So past research has shown that generally epoxy coated reinforcement will require longer development lengths than uncoated bars. So that's taken into account with this factor. The factors shown on this slide are for splitting. So this is based on the bar size. If you have a number 6 bar and smaller, then you get to reduce your development length by 0.8 or 20%. And number 7 and larger use a psi sub s factor of 1. Here's a limit for psi t times psi e needs to be less than 1.7. And the last factor here is whether you have lightweight or normal weight concrete. So you modify your equation based on your lambda factor. ACI 318 also has an excessive reinforcement modification factor. Essentially what this does is it allows you to decrease the development length if you provide excess reinforcement to what is required. So you get to multiply LD times the ratio of what's required to what's provided. So essentially, if you provide twice as much steel as you need, then you get to decrease your development length by half. This reduction is not permitted for a number of cases. You can read those here. And in general, White and McGregor, or what's now become the White textbook, they don't recommend using this factor. In general, if you provide reinforcement, you want to be able to count on that reinforcement and count on the yield strength of that reinforcement. So that's one reason. And then also, if you provide excessive reinforcement, you can actually attract additional forces to that location. So it can actually become critical when it wasn't before. So in general, ACI allows it, but you should not count on excessive reinforcement to decrease your development length. On the next couple slides, we're going to compute the development length for the bars shown, and we're going to assume that the top bars here are in tension. So we'll assume that it's a cantilevered beam that we're analyzing. We're going to use both the ACI 318 simplified and ACI 318 detailed methods and compare our results. So here, with the information we're given, we have 3 number 8 bars with a concrete strength of 4 KSI and a yield strength of 60 KSI. And our transverse steel is number 4 bars spaced at 8 inches on center. And we're also given that we have a 1.5 inch cover to our ties. For our simplified procedure, we need to determine our different modification factors. First, our top bar modification factor, psi sub t, is going to be equal to 1.3 because we have more than 12 inches of fresh concrete below the bars. So we're assuming that the concrete is cast from the top here. So the concrete's cast, so we have more than 12 inches below the horizontal bar. We have uncoated bars, so our epoxy factor is going to be equal to 1. And we have a grade 60 reinforcement, 60 KSI yield, so our psi sub g is going to be equal to 1. We can plug these values into our equation, noting that in ACI, we use units of PSI. And also we have normal weight concrete, or we're going to assume that we have normal weight concrete, so our lambda factor will be equal to 1.0. So plugging these values into our equation, and we have a number 8 bar, which has a diameter of 8/8 or 1 inch, will give us a development length equal to 62 inches. So this is our development length using the ACI simplified procedure. Next, we're going to go through the ACI detailed procedure. We'll need some of the same modification factors that we had before. So we'll still have our side teat top bar factor of 1.3, our uncoated rebar, so our epoxy factor of 1.0. Now we'll have a splitting factor of 1.0 for number 7 bars or larger. We have number 8 bars here. We still have a lambda equal to 1 for our normal weight concrete, and we still have grade 60 steel, so our psi sub g is equal to 1.0. Now we need to calculate our CB factor, which we need to calculate for our cover to top face and the bar to bar splitting plane. So our CB to the top face is going to be equal to the cover, 1.5 inches, plus the diameter of our stirrup, 0.5 inches, plus 0.5 times the diameter of our longitudinal steel, so 0.5 times 1 inch. This will give us a total value here of 2.5 inches. Next, we need our bar-to-bar CB factor. And this bar-to-bar CB factor is just going to be equal to 0.5 times the center-to-center spacing of our bars. We can find the spacing by taking our total width, B, minus 2 times our cover, so 2 times 1.5, minus 2 times the diameter of our stirrups, 0.5 inches, and then minus the diameter of our bend. So we have one radius of our bend here, one radius of our bend here. The bar is going to sit right at that radius of the bend. So radius plus radius equals the diameter of our bend. And the diameter of the bend for a stirrup here is just going to be equal to 4 times the diameter of the stirrup. So 4 times 0.5 inches. We have so that gives us the total space from the center of this bar to the center of this bar, from center to center of our outside bars. Next, we need to divide that space by the total number of spaces that we have. So we have 1, 2 spaces, or number of bars minus 1, which will give us 2, which gives us a center to center spacing of 3 inches. We can then take this times 0.5 to give us a value of 1.5. So our CB here is 1.5 for bar to bar and 2.5 for our cover to top face. So the 1.5 will control here. So this is the CB factor that we'll use. Next, we need to calculate our KTR factor. This factor is equal to 40 times A transverse divided by S times N, where all our A transverse and our N are dependent on what our splitting plane is. Here we saw on the previous slide that our splitting plane is the bar-to-bar splitting plane. So this splitting plane going across has 2 legs of reinforcement crossing it. So our A transverse is equal to 2 times the area of our bar. So 2 times 0.2 square inches for our number 4 bars. The splitting plane goes across 1, 2, 3 longitudinal bars. So our N here is equal to 3. So we have 3 bars there. And the spacing of our number 4 bars is 8 inches on center. So we have 8 inches there. So here we can see our KTR is equal to 0.667 inches. We can then plug our CB that we found on the previous slide, 1.5 inches, plus this KTR, 0.667 inches, and divide by the diameter of our longitudinal bars that we're trying to develop, 1 inch. And we'll get CB plus KTR over DB equal to 2.167 unitless. So this value here is less than our limit of 2.5. So this is the value that we'll use in our detailed development length equation. We can then plug all of our different values into our ACI detailed expression, which I do here. So note that our Fy and our F'C are both in units of PSI. So we need to make sure those are consistent. And in ACI, we use units of PSI. We have all of our other factors here and take it times 1 inch, which is the diameter of our number 8 bar. So we can see here then the development length is, using the detailed equation, is 43 inches. This is greater than our 12-inch lower limit, so we'll use 43 inches as our required development length for our straight bar in tension. We can compare this to the simplified procedure, and we can see just by using the detailed procedure, we can decrease our required development length by 19 inches. So we got a big benefit by just doing a few more calculations. On this slide, I show the development length equations for straight bars and compression. So the development of bars and compression is the maximum of these two values here. So you need to calculate both and then take the maximum. In compression, you can also use the excess reinforcement modifier, but just like in tension, you shouldn't use it. So if you provide steel, you should count on being able to develop the yield strength. The modification factors for compression development length are shown on this slide. So you can see, again, we have a lightweight modification factor dependent on if we have lightweight or normal weight concrete or if we're between the two. And we have our confining reinforcement factor, psi sub r, that takes into account if there's any or what type of reinforcement is enclosing the bars that are being developed. If you have some type of reinforcement that satisfies one of these 4 criteria, then you get to decrease your compression development length by 0.75. Otherwise, you need to use a psi sub r equal to 1.0. On the next couple slides, we'll look at the development requirements for bundled bars. Sometimes when you're designing, you won't be able to, or you won't have room for the number of bars you need to get your required steel area. So you can bundle bars together. ACI allows you to bundle up to 4 bars together. The bundled bars need to be enclosed within transverse reinforcement, at least number 4 in size for compression members. Bars larger than number 11 should not be bundled, so you need to, or you can only bundle bars number 11 or smaller. And finally, individual bars within a bundle terminated within the span of a flexure member need to be terminated at different points with at least a 40 dB stagger. So if I have bundled bars here and I'm going to terminate one within a span, I need to make sure that I stagger the termination of those bars by at least 40 times the diameter of that bar. So when I'm calculating the development length for these bundled bars, what I would do is I would calculate the development length for an individual bar, and then I would increase that development length by either a 1.2 factor or 1.33 factor, so either a 20% or 33% increase, depending on if I have a 3-bar or 4-bar bundle. So again, you calculate the development length using individual bars, and then you magnify that development length based on your bundle size. A unit of bundle bars should be treated as a single bar with a diameter equal to or I guess an equivalent diameter based on the area for these specific code provisions. So for the spacing limitations, you use an equivalent bar area. For cover requirements based on dB, you use this equivalent area. For spacing and cover terms, you use this equivalent area. Confinement terms, equivalent area. And your size sub E factor, use this equivalent area. And again, the equivalent area, you take your total area and of your bundled bars times 4 divided by pi square root to get your equivalent diameter. If there is an insufficient development length available for a straight bar, then typically you'll either use a hooked bar with a 180 or 90 degree hook, or a headed bar where you can have a mechanical head on the end of these bars. The hook requirements for longitudinal bars are shown on this slide. You can see here the bend diameter and the required length of the leg shown here. So the minimum bend diameters for our longitudinal bars are based on our bar size and vary between between 6 times the diameter of the bar and 10 times the diameter of the bar. The hook requirements for stirrups and ties are shown on this slide. You can see we have different requirements, whether we have a 90-degree bar, less than number 5s, or number 6 to number 8 bars. And also if we have a 135 degree hook for less than number 8 bars, then you can see the required leg extension of 6 times the diameter of the bar. You can also see the minimum bend diameter is shown here. So for number 3s through number 5s, 4 times the diameter of the bar, and for number 6s through number 8s, 6 times the diameter of the bar. A standard hook consists of the hook itself, which we defined on the last couple slides, plus the straight length. The total required development length for a hooked bar goes from the back of the hook to the point on the straight bar at which you'll reach Fy. And we can calculate the required development length using this equation here from ACI 318. The required development length also needs to be greater than or equal to 8 times the diameter of the bar and greater than or equal to 6 inches. So 6 inches is our minimum value here. Some of the modification factors for our hook development length equation are shown here. First, we have a lightweight modification factor depending on if we have lightweight concrete or normal weight concrete. Next, we have our epoxy factor. So similar to before, where if we have epoxy coated or zinc and epoxy dual coated reinforcement, we magnify our required development length by 20%, so times 1.2. Uncoated bars is 1.0 here. Next, we have a location factor, and this has to do with the location of the hook in our section. So if we have a hook that terminates inside a column core with a side cover greater than 2.5, or with a side cover normal to a plane of hook greater than or equal to 6 times the diameter of the bar, then we can reduce the our required development length by 30%. So we use a 0.7 modification factor. Otherwise, we have a size sub O here of 1.0. Our last two modification factors shown here are the confining reinforcement modification factor and the concrete strength modification factor. The confining reinforcement factor takes into account what type of transverse reinforcement is around the hook. So if we have a hook that's number 11 or smaller with an A sub TH greater than or equal to 0.4 A sub HS, or a spacing greater than or equal to 6 dB, where S is the minimum center to center spacing of the hook and dB is the diameter of the hook, then we use a value of 1.0. Our A sub HS is the total cross-sectional area of the hook or headed bar being developed at the critical section. And we'll look at on the next couple slides what the A sub TH is. Otherwise here we'll use a factor of 1.6. The concrete strength factor here depends on if we have a strength less than or greater than 6 KSI or 6,000 PSI. So you can see if we're less than 6 KSI, we use the equation shown here, F prime C in PSI divided by 15,000 plus 6. If we have a strength greater than 6,000 PSI, then our factor is just equal to 1. This slide has the full definition of what you can count for your A sub TH. It can consist of either what's shown in the A definition or the B definition here. So either ties that enclose the hook, ties or stirrups that enclose the hook, or other reinforcement that encloses the hook in the direction of the bar in tension. So on the next slide, I'll have some figures to kind of lay out these definitions, but here are the full definitions for you to read. So this requirement equates to the following two options for confining reinforcement. You can either have confining reinforcement parallel to the bar being developed. So here's our bar being developed, here's our hook, and our confining reinforcement is parallel to this bar being developed and encloses the hook here. And this reinforcement prevents the hook from kicking out on the backside, which is one type of failure mechanism that can happen with these hooks. The other option is to have confining reinforcement perpendicular to the bar being developed. So here's the bar being developed, perpendicular to that we have these vertical ties. So this reinforcement helps to confine this bar being developed right here. So both of these types of confining reinforcement will improve the behavior of this the hook development, so it'll decrease the development length required. This slide describes some additional requirements for our hook development. Essentially, hooks where you have small cover outside the hook, so where your cover to the hook is less than 2.5 inches, we need to satisfy the following two requirements. The first one here is that our hook needs to be enclosed along the entire development length within ties or stirrups perpendicular to the development less than this spacing, with an S less than or equal to 3 times dB. We also need to make sure that the first tie or stirrup encloses the bent portion of the hook within 2 dB of the outside of the bend. So we'll look at both of these in a figure on the next slide. This provision is essentially here because hooked bars are especially susceptible to concrete splitting failures if you have small cover. So we need to make sure that if you do have small cover, you have reinforcement to prevent that splitting failure. The provision applies to the ends of simply supported beams, the free ends of cantilevers, and any exterior joints for members framing into a joint where members do not extend beyond the joint. So the outside where a beam frames into a column. So this requirement equates to the following figure shown here. Essentially, if you have cover less than 2.5 inches, then you need to provide these ties or stirrups within the development length of the hook, with the first stirrup starting within 2 dB from the outside of that back hook. So this is a visualization of what the requirement shown on the last slide is. On the next couple slides, we're going to go through an example where we have a number 11 bar embedded in the wall. And what we want to do is we want to calculate the minimum required wall thickness if we use a straight bar and if we use a standard hook, where we calculate the straight bar development using the ACI detailed procedure and the hooked bar using the ACI hooked bar expressions. We need to make sure that we can develop Fy right at the edge of the wall. The development length for the straight bar can be found using the equations on this slide. First, we need to determine our different modification factors. We don't have any information, so we're going to assume that we have a non-epoxy coated reinforcement. We're going to assume a splitting factor and a lambda of 1.0. There appears to be more than 12 inches below this, so we're going to assume that we have a top bar factor of 1.3. And again, we're going to assume that we have grade 60 reinforcement, so our psi sub g factor is 1.0. For a solid block of concrete without any side cover restrictions, typically the CB plus KTR over DB factor is going to be equal to 2. So we're going to assume here that is equal to 2. We can plug all these values into our development length expression, where we have the diameter of our number 11 bar. And we'll get a development length for our number 11 bar of 52.2 inches. This is greater than our 12-inch minimum, so we can use 52.2. And we were given in the problem that we want 2 inches of cover between the back of the bar and the edge of the wall. So the minimum thickness of our wall would be 54.2 inches to be able to develop the bar using a straight bar detail. way you calculate the development length or required development length for our standard hook is shown on this slide. The first thing that we would need to do is determine all of our modification factors. So you can see here where we have non-epoxy coated reinforcement and normal weight concrete, so factor 1.0. We have a side cover normal to the plane is greater than 6 dB because, yep, we have, right, it's a tall wall, so that's okay. So our psi sub O factor is 0.7. We don't have any information on reinforcement surrounding the hook, so we're going to assume a confinement factor here of 1.6. And our concrete, we have 4,000 PSI concrete, so we have a factor here of 0.87. Because we're less than 6 KSI, we use the equation as shown here. We can plug all these values into our development length equation, and we can calculate and find required development length of 28.1 inches. So this is greater than our two minimum values, and we can then figure out our minimum wall thickness is the development length 28.1 plus our 2 inches from the back of the hook to the edge of the wall. So that'll give us a minimum wall thickness here of 30.1 inches. Note that if we did provide confinement reinforcement around our hook, we would be able to reduce our development length by 60%. So go from 1.6 to 1.0 for our psi sub R factor. So you can see here a summary of our results. So with a straight bar, we would need a wall thickness of 54.2 inches. And with a hooked bar, we would need a thickness of 30.1 inches. And so you can see there's already a big decrease in required wall thickness if we go to a hook bar. But note that we would be able to decrease this even further, going from that psi factor of 1.6 to 1.0 if we did provide some confining reinforcement around the hook, either perpendicular or parallel to the bar being developed. So in summary here, we're able to greatly decrease the required development length and the required wall thickness by using hooked reinforcement. On the next few slides, we're going to talk about splicing reinforcement. So typical reinforcing bars have a maximum length of 40 feet. So if you are constructing a member that's longer than 40 feet in length, you'll typically need to splice reinforcement together. You may also need to splice reinforcement together when constructing a building where it's kind of constructed by story. So you'll have reinforcement extending from the wall or column below that you'll need to splice with the reinforcement of the wall or column of the next story. So those are two instances, and the other is, splicing may also be needed for assemblies that are in separate sections or to reduce transportation issues. So sometimes if you have precast sections or things like that, you'll need to splice the sections together and splice reinforcement together. There are three primary types of splices: lap splices, mechanical splices, and welded splices. Lap splices are when you have two overlapping bars that are possibly tied together. And so you can see we have one bar extending here, one bar extending here, and they overlap by some distance. Lap splices are more forgiving to field adjustments. So they're one of the most common type of splice, but they should be staggered to reduce congestion. So if you have all your lap splices in one region, you can see twice the number of bars, which can really congest a part of your column. So some drawbacks to these include bar waste, because you have all this extra bar on each side, and congestion, because you need to extend each bar a certain length. Mechanical splices are when you have two bars physically connected together by some type of mechanical coupler. You can see here this coupler has some mechanical screws here in the end, so you extend the reinforcement in, and the screw bears against the reinforcement and kind of clamps everything together. So the pro is that there's a very small or no overlap, and they're extremely strong, but they will require some tighter construction tolerances because you need to have the bars line up perfectly with each other. Welded splices are when two bars are physically connected by welding. Some of the major drawbacks here are you need a certified welder in the field to weld the two bars together, which can be expensive and can stall a project. Also, the steel that you use then must be designed for welding, which means it must be A706. So you need different reinforcement, and you need to make sure that that weldable reinforcement gets installed in the correct locations where you will have the welded splices. The other drawback is just tight welding specifications in general. So in general, a welded splice is not an ideal splice location for the field. As I mentioned, our tension lap splices are our most common type of splice. So we're going to go through the ACI 318 procedure for calculating the splice length. The first is that the maximum spacing between our bars for it to be a lap splice needs to be, so our max spacing needs to be less than the minimum of 1/5 our splice length, our required splice length, and 6 inches. So this is for our center to center spacing. Note that for number 11 bars and smaller, our lap splices are typically going to fail by splitting of the surrounding concrete. This is more likely to occur when steel stress is high and when the bars lying close to each other are spliced. So the splitting type of failure is our most likely type of failure for our lap splices. The minimum length of our lap splice depends on the type of, or the class of splice that we have, whether we have a class A or a class B splice. You can find whether you have a class A or class B splice using the table shown here. So if you have greater than twice the reinforcement required provided, and your maximum percent of your area or your area steel is spliced within the required length is less than 50%, then you can have a class A splice. Otherwise, you have a class B splice. I'm going to talk more about what this requirement is on the next slide. If you have all of your reinforcements spliced in the same location, shown here on the left, then you're always going to have a class B splice, as we saw in the previous table. If you have multiple splice points, that makes it so that less than 50% of our area is spliced within the required lap length. So, here you can see we have only 2 bars spliced, 2 bars spliced, 2 bars spliced in 3 different locations. Then this is the requirement where you can have a class A splice as long as the amount of steel provided is greater than twice the amount of steel that's required. So if you have a class A splice, then your required splice length in tension is equal to 1 times the required development length of the bar that you're splicing, greater than 12 inches. If you have a class B splice, then your required splice length in tension is 1.3 times your required development length of the bar that you're splicing, again, greater than 12 inches. So you can use these two equations with the simplified or detailed formulas for your development length to calculate your required splice length of a class A or class B splice. The required compression lap splice lengths are shown on this slide, and they depend on the yield strength of our bar that we're splicing. So whether we're less than or equal to 60 KSI, between 60 and 80 KSI, or greater than 80 KSI, we use one of these 3 equations here. And note that if we have a concrete strength less than 3 KSI, we need to increase our development length, so increase our splice length here by 1/3. On the next few slides, we're going to go through a lap splice example. And in this example, we're going to assume that we or suppose that we have a continuous beam with two number 9 bars as negative moment reinforcement, and we need to splice these bars over the support. So we want to design the splice. So we're given two number 9 bars with an F prime C, a concrete strength of 4 KSI, a yield strength of the number 9 bars of 60 KSI. We have number 4 bars spaced at 8 inches on center and 1.5 inches to our cover. And we're assuming that we have an area of steel that's provided about equal to the area of steel that's required. So this will automatically mean that we have a Class B splice. So you can see our section has a 12-inch width and a 20-inch height. We'll use the ACI 318 detailed formula to calculate our development length, which means that we need to first determine all of our different modification factors. We have a top bar factor equal to 1.3 because we have more than 12 inches of fresh concrete below the bars. Our epoxy coated bar factor is 1.0 for uncoated bars. Our splitting factor is 1.0. Our number 9 bars are greater than, or number 7, splitting factor 1.0 for number 7 bars and larger, which is what we have with our number 9 bars. And then our lightweight concrete factor is 1.0 for normal weight concrete. And our reinforcement grade factor is 1.0 for grade 60 reinforcement. Our CB factor I find on this slide. So we need to calculate our cover to top face factor and our bar to bar CB factor. So our cover to top face factor, we have our cover, 1.5 inches, plus our diameter of our stirrup or tie, 0.5 inches, plus half of the diameter of our number 9 bar, so 0.5 times 1.128, will give us a CB, cover to top face, of 2.56 inches. Our bar to bar factor is going to be equal to 0.5 times the center to center spacing. So here our B is 12 inches, 1.5 inch cover on each side, so 2 times 1.5, minus 2 times the diameter of our stirrups or ties, so 2 times 0.5 inches, and then minus the diameter of our bend, so the distance from the outside to the center of the bend of our stirrup, which is where the center of this bar is going to sit. So the diameter of our bend is 4 times the diameter of our stirrup, so 4 times 0.5. We divide all that by the number of bars minus 1, which equals the number of spaces here. So 2 minus 1 is 1, or 1 space. And we'll get a center to center spacing here of 6 inches. So half of that is 3 inches. So we can see that the cover to top face controls. So our CB here is equal to 2.56 inches. We can next calculate our KTR factor based on where our splitting plane is. So we found from our CB factor on the previous slide that our splitting plane is going to be from the bar to the top face. So there's one bar, or one leg of our transverse reinforcement that crosses our splitting plane, and there's one longitudinal bar that's involved in that splitting plane. So our transverse reinforcement is just going to equal the area of our transverse bar, the area of our number 4 bar, so 1 times 0.2 square inches. And we only have 1 bar involved in this splitting crack, so our end's equal to 1 bar here. The spacing of our bars is 8 inches, so we can solve for KTR, and it equals 1 inch. Our CB plus KTR divided by DB is equal to 3.16, which is greater than 2.5, so we're going to use a 2.5 here. Then plugging all these values, or this 2.5, into our development length equation with all of our modification factors, our 60,000 PSI steel and 4,000 PSI concrete, we can find a required development length of 41.73 inches for our number 9 bars. This is greater than 12 inches, which is our lower limit for development. So this is the required development for our number 9 bar. Our splice length then is equal to 1.3 times this development length because we have a Class B splice. So 1.3 times the 41.73 is equal to the required splice length of 54.25 inches. Shown on this slide are some additional references related to bond and development of reinforcement in typical reinforced concrete structures. And that concludes this lecture.